All right, everybody. Welcome to Unit 7.3. So today we're going to be practicing more with average rate of change and instantaneous rate of change. And we're just going to do it for real life situations. So that means word problems. Okay, so let's review first what our formulas are for each type of problem. Okay, so for average, remember, we're essentially finding the slope. So we're doing f of b minus f of a over b minus a. Okay, and for instantaneous, okay, we're using that slope limit formula. So we want to just pay careful attention to the wording for each problem so we know which formula we should be using. All right, so our first example. Okay, the distance in miles that a runner competing in the Boston Marathon has traveled after a certain time t in hours can be found by f of t equals negative 1.3 t squared plus 12t. What is the runner's average velocity between the second and the third hour of the race? Okay, so we're finding average here, so we're using that slope formula. Okay, and the second hour is our first value, and the third hour is our second. Okay, so that means that we're doing f of 2 and f of 3 as our a and b value. Okay, so plugging those into the function, we get out each of those y values. Okay, so we set up our slope formula, and now we just solve. Okay, so the runner's average velocity between the second and the third hour was 5.5 miles per hour. Okay, that was his average pace. Okay, so that one is pretty easy. Pulled out that keyword of average, okay, but you do have to evaluate the second and the third hours into the function. That's how you get your f of b and your f of a. So you have to do a little bit of, algebra arithmetic before you can apply the formula. Okay, our second example here. All right, a little bit more of an application problem. Maybe a little bit more involved. Okay, because I can already see instantaneous velocity. All right, so a baseball is dropped from the top of the building. The height of the baseball in feet. So this is the height in feet after t seconds. Okay, so this expression here, this function represents height. It's important. Okay, so find the instantaneous velocity at 5 seconds. Okay, so instantaneous means that we're using that limit formula. Okay, and it says v of t here. Okay, because it's t seconds. So it's not really changing the functionality of the formula here by making it a v and a t from an f and an x. Okay, we're going to do the same thing. All right, so I have a specific value of 5. All right, so I need my function. Just going to copy that over. All right, so the first thing I need to do is calculate f of 5 and f of 5 plus h. Right, we need that for our limit formula. So we're going to plug those in. Remember, as always, this gets FOILed. Okay, so I didn't show my FOIL separately. All right, and then you can combine those, and we're gonna distribute that negative 16. Okay, and then you'll combine all of your like terms. All right, so this is 10h I'm gonna distribute, and then remember to incorporate that 1936. Okay. You can always pause, make sure that you can work that out. I mean, again, that's just simple algebra. All right, so we're going to plug all of this into the limit. Okay, so this is our f of 5 plus h minus our f of 5 all over h. All right, so I'm going to simplify those. They cancel out. And I can cancel out those h's. So I have negative 160 minus 16h. All right, so I'm ready to evaluate the limit here using direct substitution. That means to just plug in 0. That will cancel. So I get negative 160. Okay, that is my velocity. Okay, that's the instantaneous velocity at 5 seconds. Okay. That was part A of the problem. Okay, let's bring back the question. All right. So part B says, when does the ball hit the ground? Well, if we think about that logically, when something hits the ground at a height of 0. Okay, so we need an expression that models height right now so that I can substitute in a specific height of 0. Well, the original function models height. So I'm going to take the original function and I'm going to plug in 0 because f of t, f is the height in feet, right? We're not going to plug 0 into t because that would be the time. And this is asking for the when. Okay, so we're plugging 0 into the original function because that models height, and we're plugging it in for f of t rather than t because t models time. The question is asking, when does the ball hit the ground, which implies we should be solving for a t. Okay, so I would subtract 1936 to the other side. I'm going to divide by -16. Okay, I'm trying to solve for t, which means I'm going to take the square root. So I get plus or minus 11 equals t. Well, remember that t represents a time. So positive 11 seconds and negative 11 seconds. Well, obviously a negative time does not make sense. So we're just going to say that t is the positive. Okay, so that's 11 seconds when the ball hits the ground. That's the time when the ball hits the ground. So we need to use that answer that we just solved for part C. Okay, so part C says, what is the velocity when it hits the ground? Okay, so we just found that. We have to use t equals 11. If it wants the velocity at that specific time, then we're looking for the instantaneous velocity, which means that we're going to do the limit formula again. Now we're doing the limit formula twice here for two specific x values. You could have just done it once right off the bat, like if you had read the whole question first and realized that you were going to have to do it for two specific values, you could have found the expression and then just went back to that each time, and that's option 2. All right, so we're going to first find f of 11 and then f of 11 plus h. All right, so we already know that when we plug 11 into this expression, that we get 0, right? Because that's what we solved for, but we'll plug it in anyway. And then we're going to plug in 11 plus h. Okay, remember that gets FOILed. Okay, we'll distribute the negative 16 and then combine like terms. Okay, so that turns into 1936. Okay, so we have our two values here. So now we'll just plug them into the limit. Okay, well, this is just going to cancel out. I see I can simplify an h from each term. Okay, I'm left with negative 352 minus 16h. Ready to evaluate the limit there. Which just means plug in h equals 0. That cancels. At negative 352. So what is that? That's the velocity at 11 seconds when it hits the ground. Okay, I want to do one more problem here. We're actually going to write the general expression for the slope of the tangent line, like I was just referring to in that last problem. Okay, so rather than doing the limit formula for t equals 1, t equals 2, and t equals 3 here, we're going to find the expression and then plug each one of those in. Okay, it's a lot less work. It's more direct for what we're trying to do. So the distance in feet of a water rocket from the ground after t seconds is given by s of t. Okay, find the expression for the instantaneous velocity. So whenever it says expression, right, that's when you're using the general of f of x and f of x plus h. We're not plugging in a specific x value. Okay, so f of x is just the original function. F of x plus h means we take the original function and we plug in x plus h to each of those variables. Okay, so I got a couple things going on here. I'm going to distribute this one. I'm going to FOIL this one. Okay, I'll have to distribute the 16, clean it up, combine some like terms. This is 2xh. Okay, so when I distribute, we get negative 32xh. Okay, so notice none of these are like terms. I have x an h, an x squared, an xh, and an h squared. So unfortunately, I have to keep all of those terms for right now. Okay, and I'm actually going to change this. This is f of x. So I'm just going to make these x's because I didn't carry through the t over here. I need them all to be in the same variable. There's just a variable change. I didn't change any values or anything like that. Okay, so I'm going to plug these values into my limit formula. All right. It looks worse than it is. A lot of these terms are going to cancel out. Okay, I'm going to make sure I put parentheses here because this has two terms. So I want to make sure that gets distributed because otherwise my terms are not going to cancel out the way that they're meant to. Okay, give myself some more space here. All right, so let's see what's going to cancel. So this 90x, this is going to become minus 90x. Negative 16x squared, this is going to become plus. Those are all gone. Okay, that's just from combining like terms and canceling in the numerator. And now I see each of these has an x, or not an x, I'm sorry, has an h. I'm going to simplify that out. And now I can apply the limit here. I can use direct substitution. Okay, so the expression for the slope is going to come from 90 minus 32x minus 16 times 0, which will cancel. Okay, so here's my equation for the slope of the tangent line or the velocity to any point. All right, so they were asking for t equals 1, t equals 2, t equals 3 seconds. Okay, so that just means we are plugging each one of these in. Okay, so it goes much quicker to find the velocity at multiple points if we have the expression, so that this way I don't have to do the limit formula multiple times. Okay, so this is no new concept here. We were just practicing our limit formula and our average rate of change formula through word problems. Okay. If you need to rewind at any point, just make sure that you have your full example notes down. Okay, we're going to do some practice together in class. Take care of any questions you have at that time. All right, I will see you guys soon. Thank you so much for watching.